Hello and welcome back to machine learning. In this video, we are going to study the multiple linear regression, the polynomial regression, the logistic regression, and the maximum likelihood estimation. So these are the other four kinds of regressions that we have other than the simple linear regression that we saw in the previous video. So let's begin. We'll start with the multiple linear regression. In a multiple linear regression model, two or more independent variables, that is, predictors, are involved in the model. So instead of one value of x, instead of one column acting as x, we will have several x values like x1, x2, x3 for the different columns. For simple linear regression, we can predict the price of a property using the area of a property, right? We could do that by checking the area of a property. We could make predictions about the price of that property. But there are other conditions like location, floor, which floor it is on, the number of years since the purchase, the amenities available over there. All these things are also important predictors while you are predicting the price of a property. So you should not ignore all this. They should also be included in prediction of price, which is why we need multiple linear regression. Thus, if we consider the price of property in dollars as the dependent variable and area of the property in square meters, location, floor, number of years since purchase, and amenities available as all the independent variables, then we can have a multiple linear regression, which is as below. So you have price of the property, which is equal to the area of the property, location, floor, aging, amenities, all these factors together are going to predict the price. So it's a multiple linear regression. When it's only area and price, it is simple linear regression. Multiple regression for estimating equation when there are n predictor variables is as follows. So the equation changes. It's not just y equal to ax plus b anymore. It has changed because there are many predictors now. So the equation will look like this. Y is equal to a plus b1x1 plus b2x2 plus b3x3 and so on for as many predictors as you have. So this equation is different because you have x1, x2, x3 or so many predictors. Let's now talk about the polynomial regression. So polynomial regression is the extension of the simple linear model where you add extra predictors obtained by raising each of the original predictors to a power, which means you're actually squaring it. So this is polynomial regression is different, but it is an extension of the simple linear regression, which means you will have one predictor, one dependent variable, but you will add extra predictors by by squaring the power. So how does that work? For example, if you have three variables, x, x2, and x3, and you want to use them for as predictors, then it provides a simple way to do that by yielding a non-linear fit to data. Okay, so this is what it looks like. This is the equation. Fx is equal to c0 plus c1x1, c2x2 plus c3x3. This is in the above equation. You have c0, c1, c2, c3. They are all coefficients. And this is what the line looks like. So in multiple linear regression, we are still trying to fit actually, it's not over here, it's not x1, it's actually x raised to 1. This is x squared, this is x cube, okay? So in polynomial regression, we are dealing with a curved line instead of a straight line, okay? In linear regression, what happens? You have a straight line that is able to help you to predict. But in polynomial regression, it is used when you have data that does not really fit onto a straight line. Okay, when creating a straight line is not actually giving you good accuracy, which is when you will try to create a curved line instead. So when you're creating a curved line, then you're using polynomial regression, and this time you will have x, x squared, and x cubed. Consider these things as x squared and x cubed with their coefficients. So you will have a curved line which looks like this. So this is a curved line. And obviously, a curved line is going to be able to fit the points, the data points better than a regression line, which is a straight line. Okay. So this is the data we had earlier in one of the previous videos about internal and external exams. We created a straight line at that time. This time it is a curved line. As you can observe, the regression line here is slightly curved and the polynomial is of degree 3. So that means we have x, x squared, and x cubed, okay, with the data points that we saw previously. And this line will curve even further if you increase the degree of the polynomial. So if you add even x raised to 4, x raised to 5, if you do that, the line will get even more curved, but your accuracy will improve. So look at this line. This has got a degree 14. Okay, there are only 15 data points, but the degree of the polynomial is 14. And you can see that the line is almost touching every single point that you see here. Okay, so which means your accuracy is going to be very good in this case. Now let's talk about the next type of regression, which is the logistic regression. So in logistic regression, you have the dependent variable y, which is binary, either 0, 1, and the independent variables x, which are all continuous in nature. Okay, by now you probably know the difference between continuous and discrete variables very clearly, because we've seen so many numericals and all for that in the previous videos. So you know what continuous variables are. And the variable y is binary, which means it can have a value of 0 or it can have a value of 1 only. It does not have, like price is not binary, price can be anything. But in logistic regression, y is going to be binary. So actually, logistic regression is used when you have some sort of a classification problem. Like you're giving some text and you want to find out, is this text favorable or not favorable? Okay, something like that. So you have a yes or no answer. That is where logistic regression comes into play. The probabilities describing the possible outcomes, okay, probability that y will be 1 or y will be 0 of a single trial, they are modeled as a logistic function of the predictor variables. In a minute, we are going to see what that logistic function is, okay? In the logistic regression model, there is no R2, or actually it's R squared, to gauge the fit of the overall model, okay? So there is no R squared error, which we earlier used in linear regression to check if the model is fitting properly or not, okay? But you do have something called a chi-square test in order to check if the logistic regression model fits the data properly or not. So there is a chi-square test, but there is no R-square test, no mean squared error to check the accuracy. The goal of the logistic regression is to predict the likelihood that y is equal to 1 instead of 0, given some values of x. So that is, if x and y have a strong positive linear relationship, the probability that a person will have a score of y equal to 1 will increase as the values of x increase. So what you're doing is predicting probabilities rather than the scores of the dependent variables. For example, you might want to predict whether or not a small project will succeed or fail on the basis of the number of years of experience of the project manager handling the project. So this is an example of logistic regression, because you want to find out success or failure type of thing, which is yes or no kind of question. And you have one predictor, which is the number of years of experience of the project manager. We presume that those project managers who have been managing projects for many years will be more likely to succeed. So it's just an assumption. And this means that as X, which is the number of years the project manager, number of years of experience of the project manager will increase, the probability of Y will also increase and will be more equal to 1. So success will be increasing, right? And if we take a hypothetical example in which 60 already executed projects were studied and the years of experience of the different project managers from 0 to 20, we could represent this tendency to increase the probability that y is equal to 1 using a graph. And to illustrate this, it is convenient to segregate the experiences into different categories, right? We don't want to use all values from 0 to 20. but we will put them in categories of 0 to 8, 9 to 16, 17 to 24, and so on. And then if you compute the mean score on y, okay, for each of these categories, you will get something like this. So for 0 to 8, you are calculating what is the score, different scores of y, and take an average. 9 to 16, take an average of y and create this type of a bifurcation. When the graph is drawn for these values of x and y, it will appear like the graph below. We'll see that graph here. So this is the graph, okay? And as you can see, as x increases, the probability that y equal to 1 is also going to increase. In other words, if the project manager has more number of years of experience, then the percentage that the products, then the chance that the project will succeed will increase. Okay, so that's what logistic regression does. And an explanation of logistic regression begins with an explanation of the logistic function, which always takes values between 0 and 1. Okay, so there's a function involved here, which is the logistic formulae, which are stated in terms of the probability that y is equal to 1. It is referred to as p, and probability that y is equal to 0 is referred to as 1 minus p. So this is what the function looks like. You will take a natural log of p upon 1 minus p. Okay, p means y is 1, 1 minus p is probability that y is 0. And this is equivalent to the equation of linear regression, which is a plus bx. Okay, now here the ln symbol, we know it's a natural log, and a plus bx we know is the regression line equation. And the probability p can be computed from the regression equation, which means instead of just giving the value of y, this time we are giving the value of this whole term. So if we know the regression equation, then we could theoretically calculate the expected probability that y will be equal to 1. So we will get some value, some probability of how possible it is for y to be 1. So this is the value of p. P is equal to this exponent is actually the e exponent raised to a plus bx upon 1 plus e raised to a plus bx. So this is the formula for calculating p. And let us say that we have a model that can predict whether a person is male or female based on their height. So given that the height of the person is 150, we need to 150 centimeters. We want to predict if the person is male or female. Now we know that the coefficients are a equal to 100 and b equal to 0.6. So this is also given to you, the values of a and b from your regression line. And using the equation that we just saw previously, we can calculate the probability that this person is going to be a male or a female. So we know this equation, right? E raised to a plus bx plus e raised to a plus divide by 1 plus e raised to a plus bx we saw earlier. We can calculate that, put all those values we just found, and you will get 0.000046. Okay, that means probability is near 0 that a person with 150 centimeter height is going to be a male. Okay. Now let's talk about some assumptions about this logistic regression. So there exists a linear relationship between the logit function and the independent variables. So that is one assumption. The function that we saw, which was natural log p upon 1 minus p, there has to be some linear relationship between the equation and between the independent variables and that function, natural log function. The dependent variable y must be categorical. Okay, that we mentioned in the beginning itself, that it should be categorical and should have a binary value. So it's not just about category, but it should have only 2 categories. So you couldn't have colors. Colors are categorical, but if you have colors like red, blue, green, yellow, logistic regression won't work. You can have only binary values like yes and no to be able to do a logistic regression. The data meets the IID criterion. Okay, what is IID? independent, identically distributed variables. So all the data should be independent as well as they should be identically distributed. So that means your error terms, epsilon, they are independent from one another and also identically distributed, preferably normal distribution. And the error term follows a binomial distribution, which looks like this. Okay, n is equal to number of records in the data, and p is equal to the probability. We already studied binomial distribution previously, so this shouldn't be very difficult to follow. Now let's talk about the last regression technique, which is the maximum likelihood estimation. So the coefficients in a logistic regression are estimated using a process called maximum likelihood estimation. So we saw that we do have coefficients A and B constants still available. So we can use those constants. We can calculate those constants using the maximum likelihood estimation. So first, let us understand what this likelihood function is before we move on to MLE. Okay, so let's say a fair coin outcome flips equally heads and tails of the same number of times, right? If you have a fair coin, you have equal chance of getting heads or tails. If you toss the coin 10 times, it is expected that 5 of those will be heads and 5 of those will be tails. That's what you expect. Let us now discuss about the probability of getting only heads as an outcome. It is 5 by 10, which is 0.5 in the above case we just saw. Whenever this number p is greater than 0.5, then you can say that this is in favor of heads. But when p is less than 0.5, then you can say it is against the outcome of getting heads. Let us represent n flips of a coin as x1, x2, x3, so on up to xn. And we can have xi, which can take the value of 1 or 0 only. So let's say xi is 1 if the outcome of the coin flip is heads. And let's say that xi is 0 if tail is the outcome of our coin flip. When we use the Bernoulli distribution, because we have one trial, two outcomes, when we use the Bernoulli distribution, each coin flip can be represented like this, right? So you have f xi given theta is equal to theta is the probability. So theta raised to xi into 1 minus theta raised to 1 minus xi. We know this very well from Bernoulli distribution, which we studied before. Okay, now this is just the same kind of equation, but different x's. So you have x1, you have xi, you have xn, depending on how many predictors you have. So here h hash, which you see here, it's the number of coin flips, right, that you're doing that resulted in the expected outcome. In this case, we are talking about heads. And the likelihood equation is given like this. L of theta given x is equal to, so likelihood equation, that's why we are using L over here. That is given by f xi given theta. And we can calculate this using the equation we just saw for all kinds of predictors, n predictors. But the likelihood function is not a probability. The likelihood for some coins may be 0.25 or 0 or even 1. What MLE is, it's about predicting the value for the parameters that maximizes the likelihood function. Okay, so you have to predict the values in such a way that this MLE is maximum. And this is the equation for that. So you take a log of this and take a log of that. It's just log added on both sides. So this is how maximum likelihood estimation works.